We're going to be learning now in section 1.4.1 a method of solving a linear differential equation. Now here's a linear differential equation because I have a y, and it's a first order. I should say this is first order. Y prime is just a plain y prime. We have a y, plain y. That makes it linear, and that makes it a differential equation. So here is our standard form: y prime plus some function of x times y equals some other function of x. That's a standard form for a differential equation. And what we want to do is over here look at the corresponding homogeneous equation, meaning that if instead of having q, I just make it 0. So this is not the original differential equation we're solving, but this is the corresponding homogeneous, or it's a homogeneous differential equation that sort of corresponds to this equation. Anyway, I want to define a new function u such that u of x is equal to y of x over y1 of x. What is y1, you ask? Y1 is the solution of this homogeneous differential equation, and it's easy to find y1 because this differential equation here is separable. So we could solve it by separating variables and separating the x's and the y's and get our solution. Anyway, once we have the y prime, y divided by y prime is now called u of x, and our goal is going to be to find u of x. Meanwhile, just by multiplying out, y, our original y, that's the y that we're trying to solve for this differential equation up here, y is going to be u, is u times y1. Again, we know what y1 is, and we want to find u, so then when I multiply it, I'll get y. Get it? Meanwhile, if I take the derivative of each side of this equation, I get y prime by product rule, y equals u prime y1 plus u y1 prime. Now, I'm going to take this and plug it into the original differential equation. So where I used to have y1 up here, now I just have u prime y1 plus u y1 prime, and where I had p of xy, now I have p of x times u y1. Now I'm going to factor out the u, and I get u prime y1 plus u times this smacker over here equals q of x. But notice that this smacker over here is equal to 0. Because why? Why is that? Because y1 by definition was a solution of the homogeneous differential equation. Get it? Cool. Now, that gives me u prime equals y1, u prime times y1 equals q of x. So u prime is equal to q of x divided by y1, which, of course, that just means that u is equal to the integral of q over y1, which, again, hopefully I can integrate that. If I can't integrate this, I'm in trouble, but well, even if I can't, I could put the solution in this method. Anyway, y is equal to y1 times q of x over y1. So y is my actual solution. The solution of the original differential equation is going to be y, and that's going to be y1, which I could find, times the integral of q over y1, which hopefully I can integrate q divided by y1. But even if I can't, we could technically, if we had to, leave the solution in this form, and this would be considered a solution to a differential equation. So, yay! Now, I just showed you why variation parameters works. I'm going to do an example in the next video to show you, well, to show you an example.